Okay, now so we will continue the last part of the spin qubit, and today we'll talk about the two qubit gate. Okay. Last time we went through some math. The whole goal is just to tell you that we already know how to do the one qubit gate very well, right? We can use more precision, use rapid oscillation, and it can form any qubit gate in principle. A single qubit gate, I mean, right? But quantum computing is nothing if you cannot do entanglement. One of the way to do entanglement is to use the C0 gate. However, in spin qubit, there are many possibilities, but it's difficult to construct a C0 gate directly. So the first thing I told you last time is that, well, we need C0 gate to form entanglement. This is just a typical circuit we learned in E125 or some more elementary quantum computing algorithm class. It can form entanglement by using Hadamard gate and control NOT gate. So the key is that how do we create a control NOT gate? And I show you that, well, you can create a control NOT gate by using a control phase shift gate, which is pi phase shift, right? So this is which is a control a Z gate actually, right? And how do you do that? You just need if you have these gates, then you just need to apply a single qubit Hadamard gate to create the control NOT gate. We went through the math, right? This is just pure matrix multiplication. So good, if we can make a control phase shift pi gate, right, then it will work. But how do we create a control phase shift pi gate or control Z gate? We can use a gate like this, okay, which is also kind of like control phase shift gate. Okay, and in this case particularly, you see that it is phase shift by I phi here, and here phase shift by I pi minus phi, right? If I have this gates, then I can create this CPS pi gate by just applying another phase shift gate, single qubit, which we know how to do it already in the spin qubit, right? To the second and the most significant and also the least significant qubit subsequently. And very often you can absorb this to other algorithm because this other parts of the algorithm, you probably don't need to implement this because this is just a single qubit phase shift gate. If before you have another Z gates, you just combine them together, right? I phase shift by pi and phi minus pi. Okay, and again, I went through the math to show you that what is I tensor product phase shift pi, and then what is phase shift phi minus pi tensor product I, and then you just try to do multiplication u times this term times this term, then you will get the control phase shift gate here, right? So in summary, if I can create this Hamiltonian, okay, I mean a gate by using a Hamiltonian, then I can create CPS pi and then eventually create the C0 gate. And that's one of the approach in the paper people publish that how they can create the entanglement, a two qubit gate. Okay, so our goal is to understand how they create this gate. Again, this gate is 1, 1, I phi, I pi minus phi, diagonal, right? So let's go back to, this paper we have not read yet, but this is from the same team who published the paper we studied for the one qubit gate. Okay, so you see it is very familiar. That is exactly the same circuit we studied last time, but it's rotated by 90 degrees, right? I don't have the slide here, but remember last time we rotate counterclockwise by 90 degrees, we have this ESR, electron spin resonance, which will pass through the AC current, right? Then you will get the AC field. So again, if I remember correctly, this is B0. So it means this is the Z direction, right? Again, we don't look at A yet, look at B. We look from the top of the wafer. Remember, last time I also do a cross-section cut along here, and I say that if you cut it, then you actually will, if I rotate it, right? If this is the wafer, Maybe this is the silicon substrate, and maybe they have some insulator. I don't know what they use, silicon dioxide. And then on top of it, right, then you will see this metal line, right, this green line, right? And then you will see this brown line here. This is the reservoir, right? And then eventually you will see this purple line, G4, right, G3, right? So just want you to make sure, if you don't understand, talk to me. This is very important, right? Know how to read the paper and see the figure. This is a top view, right? So these are the metal line. And we say that they have this control gate, I mean confinement gate, right? So basically this confinement gate will do this. It try to have the build a potential around here to confine, right, the two qubits inside, right? And so now you see that last time we only play with one qubit, now we have two qubits. But let me finish this actually. And then where is the x direction? Again, by Ampere's law, the right-hand rule, right? If you have a current going in this direction, you have this magnetic flux, magnetic field going into the wafer, right? So this can be, if you call it y, then it is y. You call it x, this is x. But the main point is you going down, then you, last time I call it x, right? You can also call it y. Going into the paper, that is the x direction, right? And that is correlated to the Bloch sphere we studied earlier. This is, you might have the x, you might have the oscillation of the magnetic field, which is B1. What do you call it? What did we call that last time? Cosine omega 1t, right? That is the magnetic field, right? Oscillating there while you have the B0z hat going up, right? And this is used for the rapid oscillation, or we call electron spin resonance. Is that okay? Right? So orient here. Now then, let's look at the two qubit. Now on top, it show another cross section, but this cross section is along here. Let me see. Let me use yellow. This is the cross section. I call it A dash. Okay. So this is A dash. Okay, so basically you go from here, you see the control gate, and then you have a gate 1, you have gate 2, and gate 3, right? So between gate 1 and gate 2, you actually form two qubits. Yeah? You just adjust the potential so that they only have two electron, right? Excess electron in these two regions. Okay, this is the cross section here, right? Just now what I did, or last time it was here. If I call this B dash, then this is B dash, right? Try to think about that, okay? Okay, so last time, so we have no problem with one single qubit, right? But if you have two qubits, how are you going to, just for one qubit operation, how are you going to selectively operate on one of them, right? So what you can do is do the so-called star effect. The star effect will change the G factor, right? And thus the resonance, right? So we keep saying that the normal frequency omega L, right, is E over MB0, but that was like we assume the G factor is 2. But in principle, it is G divided by 2, right? G usually is 2. Of course, I need to add a negative, or maybe I just put absolute value. So this star effect is done by what? By applying the gate voltage, G1 or G2. So on top of G1 and G2, I try to apply different voltage. So I create different electric field. Okay, this electric field is going to change the gyromagnetic ratio. Right? To be frank, I don't know exactly the math of doing that, right? You can study more, but the main point is that you use the voltage, different voltage here, to change their gyromagnetic ratio. And then you have different resonance frequency, and because or normal frequency, right? And because you have different normal frequency, you remember that when we do this rapid oscillation, the best is when your omega 1 equals to the normal frequency, right? So by doing this, we change different frequency of this electrical current. Then we'll have different frequency of this omega 1, which is the magnetic field in the x direction. And then we can choose which one to process, right? That is the first thing about star effect. So this is, even we don't know this well, just really understand that we can use electric field to change the Raman frequency. This is very important because in semiconductor, we know very well how to play with voltage, right? And electric field. We don't know how to do well with the spin, actually, although there's something called spintronics there. But the whole industry, the main experience is playing with the voltage. Okay, that is first thing. Now, second thing is this. Now, remember our goal is to create this matrix, right? And even simpler, we actually want to make phi 1 equals to pi minus phi 2, right? That is what we said here. If I can make them add to pi, then I can create a CPS pi easily, control C gate, and then I can create the control NOT gate, right? So again, I hope you remember, right? When I say create a gate and then another gate, the gate is all about applying a pulse to our qubit. So when we create a gate, we just apply a pulse, and then if we want to further create the CPS, we just apply 2 more pulses, right? So I hope you remember this. It's unlike the regular semiconductor chip logic gate layout that you really to physically put a gate there. So our goal is this. Now the point, the idea is this. If you just look at this matrix, it is this. First of all, maybe I need to tell you this matrix. What is the meaning of this matrix? It's talking about you have 2 qubits, so you have 4 basis states. Okay. So let me remove this one actually. Rewrite this as phi 1 equal to pi minus phi 2. These basis states are spin up, spin up, spin up, spin down, spin down, spin up, spin down, spin down. Because I have 2 qubits, isn't that I will have these 4 basis states, right? So basically, the goal here is that I want to induce a phase shift only to these 2 states, which are, we call it anti-parallel states. Because they are pointing in opposite directions, so they're anti-parallel. This is parallel. And this is also parallel. Okay? So we have a 4 basis states, right? And then, of course, the general state is the superposition of these 4 basis states. And our goal is that if I can come up with a physics, a Hamiltonian, that it will only cause a phase shift to the anti-parallel state. That is exactly what this gate is about, right? You apply to this state, you do matrix multiplication, it's just identity, apply to this state, identity, apply to the anti-parallel state, you shift the phase. You only change the phase by e to the power I phi, right? So that is the idea. So how do they do that? So it is proof that, they found out that we can do this if we do a tilted double dot. Okay, so what does it mean? If we look at AA, right, or just the potential well done at G1 and G2, it is like this. This is below G1, this is below G2. You will have a quantum well, right? And then you might have spin up, you might have spin down. So if you want to make it tilted, what it means is that, if I understand correctly, you make this one, I just assume that it is digital. You make this one, for example, lower. and the other one is still the same, right? So then this guy will have a lower energy. Do you see this? Right? So this one you really need to watch the video to understand what I'm saying. This is a tilted double well. Okay. So this get pretty messy. Let me just clean up a little bit. This part belong to this part, right? I'm talking about how to change the gyromagnetic ratio, and I forgot to say that besides using star effect, you can use micromagnet, right? Make it close so that you have different magnetic field. Then you can change the resonance frequency, and then this whole thing, right, is about this figure. Okay, and then this part or this drawing is about the tilted double well. Okay, so just take it for granted, right? So we found that if you can tilt it by this amount, but some amount which is epsilon, then you will create a phase shift only to the to this anti-parallel state. And if that is the case, I created the gates that I want. And then I can apply more pulse to create the control Z gate, and then apply more pulse to get the control NOT gate. Then I'm done with the entanglement gate. Okay? So basically, that's it. I think you already see how it works, right? But let's go deeper. Just understand a little bit more. I can be very frank to you. I don't understand all the details because I did not go through the math, right? You really need to go through the math. But we can still understand a little bit more, right? So now in our mind, we know that we have two quantum dots. We can apply different gate bias to get start shift. We can also apply gate bias to tilt it when we're doing the two-qubit operation, right? So how does it work? So in order to have a two-qubit gate, we actually need to borrow other states. We cannot just only think about having the two-qubit state we just mentioned. So here it has 6 states: spin up, spin up, spin up, spin down, spin down, spin up, spin down, spin down. And then it also have a state called 0, 2 and 2, 0. So what does it mean? You have a quantum well here. When we say spin up, spin up, spin down, we are talking about, for example, one of the well is spin up, one of the well is spin down. But it is also possible to get to have let me write this first. For example, this is called spin up, spin down. But it's also possible to have this situation. That no electron here, but both electrons are here. Okay, this is the 0, 2 state. And similarly, if both electrons on the left, then that is the 2, 0 state. In quantum computing, we don't want to operate on this state, but we are borrowing this state to realize the control NOT gate. This is similar to neutral atom we might discuss later. They borrow the Ripple state to do entanglement gate, right? Here we also borrow the space outside of the space that we're working on, and then we can do entanglement. I think this is the most important concept I want you to remember. It happened in many type of quantum computer qubit, right? But why it is so, that depends on the math, right? So I just want to discuss a little bit what is easy, right? So we use star effect So actually, we have two different Larmor frequency, right? Because we use the star effect, right? So the well one, right? For example, the quantum dot on the left, it might have the Larmor frequency, that energy, I just call it energy, EZ1, right? And then the other is EZ2, right? Just because of the star effect, right? So that's why you have different Larmor frequency, right? So again, when you it is very normal. Then what is the total energy for plus plus? If you apply the Hamiltonian, right? If it of course, let me just remind you what I mean here. Let's say this is spin up. This is I think spin up is here, right? And spin down is no, spin down is has higher energy, right? And then spin up, right? Because when spin up, then you spin up, you're at the same direction, and then no, I'm wrong. Sorry. When you are spin up, your magnetic moment is, spin up, your spin aligned with the magnetic field, but your magnetic moment is opposite of the magnetic field. Then you get negative, and then you have a further negative for the negative mu b, right? So this is spin up, this is spin down, right? Just again, Hamiltonian equal to negative mu b, mu dot b, right? And for electron, spin is opposite to mu. So if you spin up, then this is actually down, negative, right? This term is negative, opposite of this. Then you get negative, negative, you get higher energy, right? So for spin up, I call this one as the EZ. The whole thing is EZ, okay? So the spin up's the eigenvalue is EZ divided by 2, okay? And this is plus EZ 2 divided by 2, right? Because the first qubit has an energy of EZ1 divided by 2. The second qubit has an energy of EZ2 divided by 2. So this is just equals to the EZ. Right, which is the average of the Zeeman energy, right? The average of the Zeeman energy. Now, however, in the matrix given by the paper is negative, then they actually referring to a lower energy level, right? So this one we don't want to go to the try to argue with that, right? So basically, they put 0. Then basically, actually, this is not real spin up. They're actually talking about spin down. Spin down with spin up is negative. Did I say? Yeah. Yeah. So here you understand what I mean. I forgot what the papers say. If they spin down, either I'm wrong or either they are wrong, right? But it really doesn't matter. Spin up, spin down. They doesn't change the math. The main point is that they put negative. Then it means this is a lower energy state. Okay. You just let's just take this for granted. Not go to the details. I just put negative. Then this will become negative EZ, right? Yeah, I forgot what the paper put for this one, but I think they put spin up. But you know, if it's spin up, the energy should be EZ instead of negative EZ, right? But anyway, that is not important, right? How about this one? So in this case, I have a spin up. It gives negative EZ1 for the first one, and then the spin down is, because it's spin down, right? So it is, instead of negative, it comes positive, right? Just opposite direction, EZ2 divided by 2, right? So this one is just the delta divided by 2, right? So this is the difference of the splitting Larmor energy, a Zeeman energy, okay? So this is very natural, right? So I hope that you can see that. Now, then there are some terms. Let's look at this first, right? When we say we put the charge on the two well, you have Coulomb blockade. When you already have an electron, the potential increase a lot. It's more difficult to put another electron, right? So U term is just talking about the energy, right? The total energy, the energy due to Coulomb, the Coulomb energy, because you put them together. And basically saying that the system's energy is much higher, right? If you put them together. So this is the Coulomb energy, right? When they put with a two electron in a dot. Okay. But we also have this epsilon, which we just mentioned earlier, is called detuning or the tutor potential. So what is that? That is what I said earlier, right? You might have a tutor. I don't make it like gradual. I just put it like this. This difference is the epsilon. Okay. Now, of course, if you have a epsilon, then it means it's more difficult to go from left to right and more easier to go from right to left, right? That's why your energy, one of them is minus epsilon and other is plus epsilon. Okay. So that is to understand this matrix, right? Because that is the Hamiltonian. I mean, this is the we try to understand what Hamiltonian the system is, because now we allow it to go to this as states that you have the two electron in a single quantum dot, right? So that's why we construct this, and you know that the Hamiltonian determine how the state evolves. So that's why it is the quantum gate itself, right? Now, but however, we still have something T, and this is a very important. That is what enable the coupling, which is the tunneling. Okay, so what is this? I will put here. Sorry for that. T is the tunneling energy or tunneling term, right? Tunneling. What does it mean? Because you see that it couple, right? If you look at the matrix, you do matrix multiplication, it coupled the anti-parallel states to the S1, S2 states. S02 or S20, then it is very clear now, right? Because if I'm in the anti-parallel state, I have a chance to become 0, 2, or 2 state. It means one of the electron need to tunnel to another quantum dot. And that's why it's called tunneling. Okay? So why this tunneling is important? Let's look at the last slide. We have this slide. We have this Hamiltonian, right? So basically, I did not really show you how we come up with this Hamiltonian. I did not explain very well because I also have limitation. But I tell you every term, right? Qualitatively, what they mean. But the most important thing is that we have this tunneling that allow us to couple this state to this state. Why only this state? Why it does not couple the 0, 0, and I mean up, up, and down, down state, the parallel states? That is because the coupling right, is through coupling from, for example, the anti-parallel. Let me just give example. It's just instead of saying anti-parallel, up and down to S. This one is through another state, which is a singlet state, right? This state. right? We are going too deep now. It's a superposition of this anti-parallel state, but still, this is in two electrons. This is still, you have one electron on the left, one electron on the right. Okay, so you just trust me, right? Or trust the paper. The reason that you have tunneling, of course, is talking about you go from anti-parallel state, for example, up and down, to the S21 or S22. But in reality, how it achieved that is because this one has an overlap with another superposition state, S11. And from the math, you will find that these two has so-called anti-crossing. This allowed them to tunnel to go from this state to this state. However, for spin up and spin down, both spin up, up, and down, down, they don't have overlap with this S11 state, because you see that they don't have overlap, just do an inner product, right? So they won't go to the SO2, right? So as a result, that's why you only have this tunneling term. And that is the term, then you apply the Tudor potential coupled with this, right? You do some simplification, right? And that's why you only have the anti-parallel state will fill this epsilon, okay? And then you project to only the original state. So this is again up, 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 down, down, up, and down, down, right? So now we go back to our computational basis, right? So we forget all these bases that we don't want to compute. It becomes a matrix like this. And if you have a large DEZ, and if your epsilon, the Tudor potential, you apply it very fast, then you will be able to form this, right? So I see that I really did not explain everything to you in this short class. But the main concept I want you to get from this two-qubit gate is that, first, we create a gate which is not the usual gate we use for entanglement. But no problem, because we can use other single qubit gates to create the control knot from this gate. This is first thing. Second, in order to do this entanglement gate, we actually need to explore the physics outside of our space. Our space is up, up, down, 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 up, down, up, down, up, down, right? But we allow you to couple to this S states that you have two electrons in a quantum dot. That is the way that allow us to do the entanglement. Okay? And then, how does it do it? It do it through the physics that when you want to go from this state to this two spin in one quantum dot state, you actually need to couple through this superposition state. And that's why only the anti-parallel spin will fill it. And only they fill it, and that's why when you apply the Hamiltonian, you only have phase shift in the anti-parallel state. And that's why you can achieve the phase shift gates that you want, right? And the final message is this. The whole thing here is all by controlling the electronics. We use star effect. We need that in order to have a large EZ. That is important. Delta EZ, I mean, large delta EZ. We need the star effect. We also need to tune the potential, which is easy, with a fast pulse. So you can have this epsilon, you tune it very fast. Okay? And yeah, and that's it. And then we rely on the physics. The rest is too deep for me also. So I will just stop here for our two-qubit gate. And I hope you understand this. If in the future you have the chance to work in a spin qubit company, talk to the physicists, to see what they do for their entanglement gate and try to understand the physics. But I think what I taught you give you some initial hint, then you can learn deeper. Okay?